Christian Jelsch from Laboratory for Crystallography, Magnetic Resonance and Modeling at the University of Lorraine at Nancy, France. And Christian also works at CNRS. The lecture is entitled Charge Density and Intermolecular Interactions. Christian, in the years of 1983-1985, was educated in math at the preparatory school at Strasbourg. Then, since 85 to 88, he studied chemical engineering at the Ingénieur École Centrale Paris. Next, in the years 1989-1993, Christian was doing his PhD project at the CNRS Laboratory of Structural Biology at Strasbourg. Next, he went in the years 93-95, he went for postdoctoral research at Yale University, working at the molecular biology and biophysics department laboratory of the Nobel Prize winner, Professor Thomas Stapes. In the years 1995-96, Christian did a postdoctoral research at Marseille in France at CNRS. And since 96 to 2011 was CNRS researcher at the same at the laboratory at Nancy, which at that time was called Laboratory for Crystallography, Modeling of Mineral Materials and Mineral and Biological Materials. And in 2001, Christian got habilitation to direct research at the University of Henri Poincaré at Nancy. Since 2011, Christian has been a CNRS Director of Research and works at the University of Lorraine. And since 2018, he's the editor of Journal of Molecular Structure, published almost 140 papers, 4 book articles, very well cited, with very good, reception in community. And very important, as many of you know, Christian is the author of famous MoPro software, very commonly used all over the world. And his scientific interests are focused on charge density analysis, crystallographic software, electron density database development, electrostatics, physical chemistry, crystallogenesis, crystal engineering, protein crystallography, enzyme catalysis, molecular recognition. And today, Christian will present us his talk on charge density and intermolecular interactions. Christian, the screen is yours.
Hello, everybody. I would like to thank the organizers, Paulina and Christophe, for inviting me to giving a talk within this SIG of the IUCR, Quantum Crystallography. So I will have 4 main topics in my talk, and I will start with an introduction on charge density. So crystallography is a very powerful technique to determine the structure of molecules. And so at low resolution, which is achieved for proteins, generally around 2 angstrom, we can see this kind of electron density maps, where you can see atomic positions and thermal parameters can be refined isotropically. More details can be seen at atomic resolution around 1 angstrom. This kind of resolution is generally achievable for small molecules. And we see now hydrogen atoms much better. And atoms can have an anisotropic thermal motion parameters refined. Finally, we're arriving to the subatomic resolution, or called ultra-high resolution, which is in the interest of quantum crystallography. So here we see details between the atoms, such as the bonding electrodensity, and we can refine atomic charges, for example. In this community, we use a lot of the multipolar atom model, which was developed by Hansen and Coppens a while ago. And here the molecular electrodensity is modeled as a summation of the atoms of the atomic densities. The atoms are themselves decomposed in three terms: the core electrodensity, the spherical valence, which has two parameters which can be refined: the valence population and the kappa coefficient. And finally, some other terms which are multipolar, as shown in these figures below. All these multipoles are orthogonal with each other. So I would say was the signal we see in the charge density studies, the deformation of electrodensity. This is the difference between the actual density of the molecule, and we subtract the density obtained theoretically by atoms which would be neutral and spherical. So in blue, in this peptide bond plane, we see the bonding density, and on the right, two electron lone pairs on this oxygen atom. So see this kind of, so the electron accumulations are compensated, of course, by electron depletions, which are in red, like on this hydrogen atom. This kind of signal can be observed by crystallography at ultra high resolution, but it can also be computed by quantum mechanics. And also you can model it by database transfer if you don't have enough data. So I started my career as a researcher in Nancy, working on the charge density of macromolecules. It was, I started on chrombin, which did diffract very well to 0.54 angstrom. This was measured at EMBL Hamburg at Victor Ramzin's beamline. This was the first charge density of a protein, and we were able to refine a constrained charge density along the polypeptide chain. Later, we worked also on human aldose reductase, a much bigger protein, which is an enzyme. And we also were able to do some constrained refinement. This was Benoît Guillot during his PhD. We developed also electron density libraries. These enable to reconstruct the charge density of proteins, nucleic acids, but also small compounds, which are only known at normal resolution. This is done by database transfer. So there are 3 databases which have been published in the community. There is the LMAM2 published by us, which is experimental. There's the one which is theoretical, UBDB, developed at University of Buffalo, and which is now maintained and developed in Warsaw by Paulina Dominiak. And there's also Invarium, another theoretical database developed by Birko Dietrich. So in our laboratory, we have developed the MoPro suite software. So this was initially dedicated to the application of charge density to proteins, but then it was extended also for refinement of usual small molecules, and also can do database transfer. Its richness relies probably in many constraints and restraints available, and graphical user interface. MoPro Viewer, for example, is a molecular viewer and graphical user interface developed by Benoît Guillot. I would like also to pinpoint a paper which I like a lot. We published in 2018, which is a method to estimate statistical errors of properties derived from charge density modeling. So by this standard deviations of several structures which are deviating, we can compute an estimation of the error for each kind of derived properties like critical point position or electrostatic potential value, etc. I come to my second part of the talk with about rapid electrostatic energy computations. So for a while we have been computing the electrostatic energy by the EPMM method, which was first published by Volkov, Koritsantsy, and Coppens. So the electrostatic energy is the integration of the summation of electrodensity multiplied by the electrostatic potential of the other molecule. So here we have the difficulty is that we have a total electrodensity model and not just point charges, where the computation of energy is straightforward. So here we do a summation of the pair of atoms which are interacting. And at short distance, there are difficulties as there is interpenetration of the atomic electrodensities. And therefore, we do some integrations in 3D. At longer distances, it's easier to compute the energy. You use the Buckingham method, where you just need to compute the product of electrodensity and electrostatic potential moments when there is no overlap between the atoms. So this had been implemented in the MoPromo module of our software MoPro suite, but the method is very time consuming, especially for proteins. So lately, Nguyen, Kizhen, and Volkov published a very nice paper about an analytical evaluation of the electrostatic energy. This was in Acta Christ A in 2018 using the Loveday alpha function. So this has also been implemented recently in MoProViewer by Vedran Vukovic, our PhD student. I would like to mention also another remarkable paper, which is a continuation. Volkov, Nguyen and Volkov describe the calculation of energy by using the Fourier transform method. So this analytic electrostatic energy calculation has been a long road. So this applies to atomic electrodensities, which are described in terms of later functions, sum of summations. So the story started by Loveday already in 1956, and there have been several papers. And finally, the calculation was established in a software by Nguyen, Kizhen, and Volkov in 2018. So the difficulty here is that we have we have to integrate the product of two Slater functions, which have a different origins. They are the nuclear positions. And so if you want to do something analytical, you need to describe the two function in the same origin. So you use this alpha function, which is expressed with the same origin here. And as you can see, the equation on the down right is very complicated. One unique Slater function is an infinite sum, which of course converges quite rapidly, but still. So I'm not going to go into details about these equations. This is well described in the original paper of Volkov. So I'm going to talk more about the speed of electrostatic energy calculation. What is the ratio, the acceleration ratio? So we tested this on small molecules, Le Grand Kephalin, and the acceleration is about 2 orders of magnitude. For the case of a protein, this is glutathione transferase. So this study on this protein and the implementation of the analytical energy was published in Acta Christ D last year. So this is a protein ligand system where we compute energy between ligand and protein. And we see that the acceleration ratio depends on the calculation you're doing. If you have a lot of close contacts of interpenetrating atoms, you have 2 orders of magnitudes of acceleration. But when you just compute atoms which are at long distance, there is actually the APMM method is as good as it is using the Buckingham method with moments. So this glutathione S transferase is a protein from a white rod fungi. It has been studied in our laboratory by the biocrystallography group, and crystal structures with 4 ligands have been determined. These are 4 basophenols, which have some slightly different chemical groups here and there. So this was published in Scientific Reports in 2018. And they saw in that paper that when the protein takes a ligand, it becomes more stable as the denatured temperature is slightly increased by 3 to 6 degrees with a ligand. So we have looked at the electrostatic energy and at this shift of the denaturation temperature TD. And we see that globally there is a good correlation between electrostatic energy and this shift of thermal denaturation. Actually, this protein has 2 molecules per asymmetric unit. And so for each ligand, we have 2 values of the energy, and we have here in the middle the average for the 2 independent molecules. Now I'm going to talk about intermolecular contacts in terms of enrichment and electrostatic energy. So I start to define the Hirschfeld surface. This is a region of space which you can use to demilitate the border of the molecule. Basically, the inner electrodensity is equal to the exterior electrodensity from the environment. So in a computer software, in a graphical interface, you represented it by showing an ISO contour level at level h equal 1/2, where h is the ratio between the inner density divided by the total density of the interior and the exterior. So this is a view of the Hirschfeld surface for a small molecule in its crystal. So this Hirschfeld surface is actually computed in MoProViewer software, where there is a menu with many options to compute these Hirschfeld surfaces. Also in our software, we can differentiate the hydrogen atoms which are hydrophobic when they are bound to a carbon atom, or when they are hydrophilic as bound to an oxygen or nitrogen, for example. So we can compute such pictures and give these numbers. So this is the content of the Hirschfeld surface in terms of chemical species. We have here 50% of fluorine on the surface. And also we have a decomposition in terms of contacts, of interatomic contacts. So here we have also 50% of FH contacts. Now we want to look at these numbers differently. So we can compute the equivalable contacts, which are obtained from these numbers which are on the left. They are actually probability products. So this is the probability of having a contact given the probabilities you have on the left. So if you have 50% of F, you would expect to have 50% times 50%, which is 25% of FF contacts. So we compare these contacts with the actual ones and we make the ratio. And we see that some contacts are overrepresented, like the CC contacts. This can be understood when we look at this picture where we have a dimer in the crystal with some aromatic stacking. Let's say it's facing C. Also here F is facing H. And the other contact which is enriched here is FH, which is a weak hydrogen bond. All of the contacts are moderately impoverished or disfavored. So by method, we have studied classes of molecules retrieved from the Cambridge Structure database. For example, ketones here, hydrocarbons with ketone groups, and nothing else. And on this graph, we have divided the molecules on the x-axis according to their content of hydrogen atom. So on the right, we have molecules with 90% of H on the surface. And we see here on the ordinate axis the enrichment of free contacts. So the most enriched contact are the OH contacts, which are generally about moderately enriched, about 1.4, 1.2. So I must say here that we have here strong oxygen acceptor, but only weak H bond donors, which explains this only this moderate enrichment. HH contacts are slightly underrepresented, and generally oxygen contacts are avoided, as their enrichment is often 0 or close to 0. We have a similar kind of graph for alcohols, but with some differences, however. So in this case here, we have one strong hydrogen bond acceptor, the hydroxyl oxygen, but we have a strong donor and a weak donor, HO and HC actually. And so here we differentiate the strong hydrogen bond, which is in blue, and the weak hydrogen bond, which is in brown. So the strong hydrogen bond, HO, have enrichments which can reach, which can be above 10 actually. And when you have a lot of hydrogen on the surface, there is some competition. So there is less enrichment. So for OHC hydrogen bonds, they are this time slightly disfavored, contrary to the previous case with ketones, as they are in competition with the stronger hydrogen bonds. But they are present, and oxygen contacts are avoided. So I would just like to pinpoint that it's interesting also to look at outliers when you do such statistical studies. Here we had a molecule with very strong oxygen enrichment, around 8. And when you look at the structure more carefully, you see that there is here a steric clash between two hydrogen atoms, distant from only 1.2 angstrom. So actually, these two hydrogen atoms were misplaced. And if they had been placed differently, we would have here nice OHO hydrogen bonds. Now I'm going to the combination of enrichment of contacts and electrostatic energy of these contacts. So I start with a very simple class of molecules, just hydrocarbons, with only carbon and hydrogen, and therefore we have only 3 contact types. So in this graph, we have on the x-axis the enrichment of contacts, and on the y-axis we have the electrostatic energy. Each point represents a molecule, so a molecule is represented by 3 points in these 3 clusters. So the HH contacts have rather repulsive electrostatic energy, and they are here always slightly disfavored. On the other hand, CH contacts here are attractive, and they are always slightly enriched. So these are very weak hydrogen bonds, so which explains the weak enrichment. On the other hand, CC contacts here are a very small energy, close to 0, but they are generally impoverished. So the archetype of this kind of crystal packing is the benzene. This is a molecule which forms extensive CH pi interactions. And another class of molecule which we studied is chlorohydrocarbons. I have actually a study on chlorohydrocarbons in IUCR journal some years ago. Here we have averaged all the contact for each contact type. We have averaged the enrichments, and also the average. We have here average electrostatic energy. So here we see that CLH is the most favorable contact from an electrostatic point of view, and it's enriched to 1.4. On the other hand, carbon-carbon contacts have very small energy, but they are the most enriched to 1.7 typically on average. So this is due to the fact that there is a lot of heterocycle stacking with occurs. And this has been shown already before in the literature that heterocycle is very much favored. So it's very much favored also from, I would say, shape complementarity point of view. If we look at other contacts, we have HH, which is slightly repulsive and which is underrepresented. Let's look here at the chlorine-chlorine contacts. So these are apparently generally attractive. This is due, despite the fact that chlorine is an electronegative atom. So this is due to the sigma hole, which can make favorable interactions with the electronegative part of the chlorine atom. So these chlorine-chlorine atoms do form interactions, but they are slightly underrepresented. So I would comment on heterocycle stacking also. I like this paper a lot by Martinez and Iverson. It's called Rethinking the Term Pi Stacking. Pi-pi interaction, as they say, is not accurately describing forces that drive association between aromatic molecules. This is misleading, and despite this paper, we still have a lot of pi-pi stacking around today in the literature. Pi-pi electrons actually don't attract each other. Maybe pi electrons and pi holes. So they rather say that electrostatic interactions between polarized atoms of substituents are favorable. It's a typical example of heterocycle stacking with some electronegative regions which interact with electropositive regions, and vice versa here. And so the enrichment statistical analysis confirmed some previous findings by other authors in this field. I did a study with Rum Papal and Simon Grabowski recently on gallic acid hydride co-crystal, recently published. In this molecule, in the crystal forms two independent molecules in the asymmetric unit, and therefore we have two molecules, in dimers, one which forms parallel stacking, the other one anti-parallel stacking. And when we look at the scatter plot of the electrostatic energy generated by each molecule on the Hirschfeld surface between the two molecules, we see that for the parallel stacking, the potential show a high correlation of 0.55. This, of course, is not so favorable. It can be rather repulsive. On the other hand, the anti-parallel stacking is more anticorrelated when we look at the two potentials generated by the two molecules. And this is more favorable. And when we look at the Crystal Explorer decomposition of energy, we see that all the energies are pretty much similar, except the electrostatic energy, which is close to zero for the parallel stacking, but takes a significantly negative value for the anti-parallel stacking. And this is reflected in the total energy summation in black, which is stronger for the anti-parallel stacking. So this is another class of molecules which we have studied. So 104 alcohols which were retrieved from the Cambridge Structural Database. We have two clusters of points. So in green we have a cluster corresponding to OHO strong hydrogen bonds, which are enriched to significant value between 2 and 10 or even more. And these contacts are always attractive from an electrostatic point of view. On the other hand, we have on the other side of the graph, we have oxygen-oxygen contacts, which are generally absent and which are very repulsive. So the other contact types are all represented here, and some of so if you look at these, you can I would just point out what's happening for the weak hydrogen bond CHO. They are slightly attractive, much less than the strong one, but they always exist, and they are slightly moderately underrepresented to values around 0.6. Here we look at ester hydrocarbons. So this is interesting to look at because we have two different oxygen acceptors, and we can look at the competition between these. Now, on the other hand, we have here only weak hydrogen bond donors. So we have here represented the average enrichment for each contact type and the average electrostatic energy. Now here the different oxygen atom types were distinguished, and we see that there were two oxygen atom types, one carbonyl and one ether type within this ester group. So we have actually the two hydrogen bonds which are moderately enriched to values around 1.2, but one of them is much more attractive, has stronger electrostatic energy. And when we go back, so these calculations were done by database transfer from the LMAM2. And when we go back to the valence electron population in these two databases, we see that the ether oxygen atom has a valence population of 6.198 and only 6.138 for the carbonyl one. And the same trend occurs for UBDB, which is theoretical. So, and this is in accordance with stronger energy here. The other contacts, oxygen-oxygen is disfavored and repulsive. And carbon-carbon contacts are again significantly enriched despite being having a very small energy. This is an outlier among ester molecules, so here there's nothing wrong about the structure, but it's just that oxygen-oxygen contacts are very much present and even enriched to very high values, whereas some of the hydrogen bonds are rather underrepresented. So what happens here is that it's not electrostatics which is governing the formation of the crystal packing. It's rather dispersion forces, presumably, and so the shape of the molecule is very important here. It's a very elongated molecule, and also these long CH2 side chains interact with each other, and there is shape complementarity here, which plays a major role. I wanted to look also to another competition between hydrogen bonds. In this case, we have here an amide group, which has a strong hydrogen bond acceptor, namely a carbonyl CO, and another type of hydrogen bond acceptor, a nitrogen with two free lone pairs and located on an aromatic cycle. So, and here we have, however, two strong hydrogen bond donors from the amide group. And when we look at the enrichment and electrostatic energy diagram, we see here that there is a nice hierarchy. So the OHN hydrogen bond has the strongest electrostatic energy, and it's also the most enriched on average, larger than 5. Whereas the hydrogen bonds towards the nitrogen atom is has less strong and also less enriched. Then we can look at the other contacts and we see that there's a kind of continuation here. We have here the two weak hydrogen bonds, which are OHC and NHC, and they follow nicely the same train as these two strong ones. And even further, we can see here the very weak hydrogen bond, CHC, which is very weak in energy and is very slightly enriched. And again, carbon-carbon contacts are enriched with a very small energy. So this kind of results reminds us of Margaret Ether's rules. Strongest hydrogen bonds form at first, weaker donors and acceptors interact afterwards. So I looked at the literature to see if there had been some studies, some similar competition situations. There was a paper by Gerard Kleber a while ago, and he studied the case of oxygen atoms bonded to two non-H atoms, one of which is in sp2 hybridization, like we see on this aromatic ring. So we have here, and the other acceptor was a nitrogen, as shown here. And here the opposite occurs as in the previous study in the previous slide. Actually, and so they study how water interacts with these, and they found that the H of water prefers to interact with nitrogen rather than with the oxygen. This is an opposite conclusion. So this result is not based on enrichment, but more on CSD frequency, which might be not so far, and from energetic considerations. So I would also like to look at some halogenated molecules. How do halogen interactions behave in chloroether hydrocarbons? So here we have only some weak hydrogen bond donors, HC, and we have two weak hydrogen bond acceptors, oxygen ether and organic chlorine. As we see that HO is the most enriched contact, and it's also the strongest when looking at the electrostatic energy. HCl is similar, but it's just less enriched and less strong. Then we have the other contacts with again carbon-carbon quite enriched, slightly enriched, I would say, but very, very small energy. Chlorine is attractive, but it is present but slightly underrepresented. So this is the sigma Hall effect, where this electropositive lobe can interact favorably with some negative lobes, negative tores around the chlorine atom. And this has been published, of course, by several groups. Let's look also at the halogen bond between oxygen and chlorine. Now, on average, this contact appears repulsive when you look at electrostatics, but it is present and moderately underrepresented. Finally, so what time is it? If I'm not too late. So I finished with oxygen atoms, looking at the electrodensity and at the stereochemistry of hydrogen bonds. So when we were looking at some point some time ago, some chemical groups and their charge density while building the electrodensity database, we found this coumarin fluoride 14, which has two ester groups, one within a side chain and one within this aromatic group. And we saw that the deformation density was very different in the plane of the electron lone pairs for the ether group. Now the signal was not very good, especially in the side chain, as there was some quite of thermal motion here. So we also looked at results by DFT, quantum calculations, and we see that there is a very different deformation density. So the two electron lone pairs appear to have two merged lobes when you look at the isocontour levels here. And I saw this situation in several molecules later. Always when I came across a molecule with an ester and ether group, I always look and it's always confirmed. And so the oxygen atoms for very different electron densities when you look at the lone pairs plane. So I would say that ethers and esters behaved quite similarly, but within them, these groups, there are two types. When they are bound to sp3 carbon atoms, they tend to form two electron lone pairs. And when they are within aromatic cycle or bound to sp2 carbon atoms, it is more two merged lobes which appear. So carbonyl is the lone pairs are very much apart. And for the nitro group, it's even more. They are at 90 degrees. And alcohols and phenols have similar, but there is some dissimilarity, I would say. We found that alcohols have lone pairs which are slightly more separated. So these two chemical groups are very important in chemistry. They have very different pK group values, and also these they are present in serine and tyrosine, which are catalytic residues in proteins. So it's very important to know where these chemical groups. So I was wondering if this difference in the lone pairs geometry had an impact on the geometry of the hydrogen bonds which were arriving on this oxygen atom. So we look actually at the distance between the hydrogen donor interacting with the oxygen atom. We look at the distance towards the COH plane here. This is another view of this distance when we have here the lone pairs which is represented. And we saw that the alcohols and phenols have a different behavior from molecules retrieved in the Cambridge structure database. Actually, alcohols have many molecules which have a very small distance towards this plane. So this means that the hydrogen bond is really more likes to be in front of the bisectic direction of these two lone pairs here. Whereas for alcohols, there is distance maximum around 1.2 angstrom, where the oxygen atom prefers to be, like in this graph here. We have more interactions towards the lone pair. So I've pretty much finished. I would like to mention this school where there is the Crystallography, the ECM Congress in Versailles near Paris. And before there is this school, Robert Stewart School, organized in by our laboratory. So if you're a beginner in charge density and want to learn about it, you can come to this school. So I would like to thank you for your attention, and I'm ready to answer your questions.
Thank you very much, Christian, for this excellent lecture, which is now open for questions and comments.
Yes, please type your questions into the chat, or just let us know that you want to ask directly. In the meantime, I have my question, Christian. I like this work about enrichment ratios and its correlation with energies. So all that results were possible thanks to the database transfer, right? You have transferred the database and
yeah, I mean, I have sometimes like 120 alcohols, and so I can get the data, the electrodensity value only from a database. So I did it with LMAM2 because currently for me it's easier to transfer.
Mhm.
But
And you,
I guess with UBDB, probably there would be some similar results.
yeah, they are very similar. And you computed the energies for dimers or for atoms?
So
using
yeah,
contact?
maybe I was too quick about that. So I compute for each short contacts which are regarded in the enrichment. I take them into account also in the energy. So if I have, for example, three OHO hydrogen bonds, I will compute the energy between the oxygen and the hydrogen which are in contact. Well, I won't compute the energy for the OHO, the free atoms now. Or if I have energy between chlorine and chlorine, I will take just the two chlorine atoms. So this is not the total energy of the dimer, of course. It's just a very partial contribution. And also it's not the total energy neither, of course. And then you can average these values, of course, over the atoms and even over the molecules.
Have you done this kind of study for a ligand interacting with protein? Have you thought that you can do it?
Yeah, we can do it. Yeah, I did some enrichment studies on proteins, and but I haven't published it. But yeah, it gives some nice results also. Yeah. So if anybody is interested, I would be happy to work on that.
Christian, in the case of this macromolecular protein applications, what kind of quality of macromolecular data would you expect in order to have, say, sound results, final results of the transport?
I think for proteins generally you can. There are a lot of hydrogen atoms where even when you do database transfer, you are supposed to model the hydrogen atoms. So you can most of hydrogen atoms are just modeled because we know where they are pretty much like a CH2 group, a CH group, or even CH3 group, even if it can rotate. It will not be that wrong. But of course, there are OH group which can rotate. This needs to be carefully modeled. Well, I've worked on some protein ligand complexes, and so sometimes it's not well oriented. So yeah, you have to check maybe your structure before making conclusion. So, but then the hydrogen atom. So I don't know if the programs which place the hydrogen atoms, if they do some intelligent placement when there are several possibilities. But sometimes you can guess where the hydrogen atom has the most chance to be, especially when there is a possibility of a hydrogen bond towards a given direction.
But would you expect any, say, resolution threshold for macromolecular data? I mean, would you?
Well, if you have a B factor about 20, this means an error of about 0.5 angstrom, I think. Well, I mean, it's always better to have high resolution, but I mean, there are these guys doing molecular docking. They don't even care about the resolution. They suppose that their structure is correct. Also, if you don't believe in the structure, you can always do an energy minimization or molecular dynamics. Well, I don't know. I would generally. I know that you have to check. You have to check the hydrogen atom positioning both on the ligand and both on the protein. Also, you have to check the pK, or the protonation state of some groups. For example, if you have a histidine, you really need to be sure you have made the right choice because it can be protonated or not. So I don't know if there are programs to do this or to do all this automatically. But a lot of people are doing some drug design, virtual screening, and they don't really care about resolution. I mean, when you do big studies, there's the law of big numbers. when you have approximate results but have a lot of data, you still get something out of it, I assume.
Big numbers, but also big errors.
Yeah.
We have a question from Hans Birgi. Are enrichments based on the number of contacts only, or are they also weighted by the atomic surface on the Hirschfeld surface?
No, I would say that they are actually we are not counting the number of contacts. They are more based actually on the surface. Yeah, it's a summation of surface. Yeah, so it's pretty much the same as in Crystal Explorer, which I think adds up surfaces, but we don't exactly get the same numbers because maybe the algorithm at some point is not, the electron density might not be exactly the same, and the way he computes and we compute the external density might not be the same also. There are the numbers not strictly equal, yeah, but it's the same number, the same methodology.
We have another question from Saravanan Kandasamy. Is it possible to calculate electrostatic energy for docked complex and each binding site residue with the target ligand molecule?
Yeah, it is very possible. Actually, I have a project where I'm doing that to compare different docked ligands, and you can, of course, use these databases. And now, where the protein generates, all atom types are present, but for ligands you might have some atoms missing, so you might need to do some approximate, maybe take an atom which is approximately similar if necessary, or you can do a quantum calculation also on the compound if you're really interested in a compound which is in the late stage of a drug design project.
Yeah, we can see that Hans Birgi is writing a question.
Oh yeah, I see.
Yeah, we have next one.
Are such energy
Yeah, are such energies meaningful? They would not consider reorganization and polarization energy?
Yeah, I must say that this is the first step. This is electrostatic energy, and this paper is not published yet. It's ready to be published. Yeah, maybe the next step is to also do some maybe UBDB and polarization or environment polarization. That's some probably the next step to do. Yeah.
Okay.
One step after the other.
Thank you very much, Christian. As we do not see anybody writing now question, thank you very much for your excellent lecture.